So, so far, when we've been talking about parameterized algorithms and tried to design them, the question has most of the time been, can you make an FPT algorithm at all? And if you could make an FPT algorithm, it was always, you were trying to make it as fast as possible, where as fast as possible meant the smallest possible f of k, right? So 2 to the k is better than k to the k. 2 to the square root k is better than 2 to the k. However, this is not entirely, or this is rather quite far from the entire picture. It's about half the picture, because the running time of a parameterized algorithm has two parts. The f of k and the n to the c, or the parameter dependence and the polynomial factor. And so far, we've only optimized one of them without caring about the other. In particular, sort of once, even when we have optimized the f of k, we have even hidden the polynomial factor sometimes into the big O star notation. So to pretend like it isn't there at all. However, it really is there, right? When you try to either program things and see how it runs, or try to do the math, I mean, the philosophy is that k is something really small, but f of k is an exponential function. At the same time, the input size n could be really big, n to the c is a polynomial. So a polynomial of something really big could easily be comparable or even bigger than an exponential function of something small, right? So actually both of them matter. Other than sort of the salesman argument that both matter, there's also the theoretical argument that both matter, or rather that maybe one should just even look at the polynomial factor and completely forget about the f of k. So there's actually quite a bit of research that have gone into optimizing the c in n to the c, completely forgetting about f of k. And why is that? So suppose you have an algorithm with running time f of k times n, then he is linear for every fixed value of k, right? So if you treat the parameter as a constant, you can phrase your theorems as a linear time algorithm for almost planarity, or for almost DAGs, and so on, right? Or a quadratic algorithm if it runs in n squared, right? And then you aren't even mentioning the f of k at all. Yes. So from the perspective of k being a constant, then suddenly the f of k gets hidden in the big O notation, and you shouldn't even care about it. But of course, the truth is that both of them are important. I would say that that's sort of obvious. However, if you look at the research that has been done, up until a few years ago, most of the research really tried optimizing one, forgetting about the other. There has been more, maybe it's like on the order of magnitude of like 10, 15 papers now that are actually trying to optimize both. And today I'm going to be talking about one of them, namely the only one that I thought was in the intersection of interesting and teachable. Nevertheless, it's sort of an ambitious talk, because I am going to spend my entire talk trying to prove one single result. So this will get slightly heavy, but hopefully the pretty pictures will guide you along anyway. Before I go there, I can tell you that once you start caring about both the polynomial factor, n to the c, and the dependence on the parameter, there is no reason to restrict yourself anymore to NP-hard problems. There's no reason to only look at NP-hard problems and ask for algorithms that run in time f of k n to the c. You can now do this for problems that are solvable in polynomial time as well. Because if the best algorithm for your problem has running time n cubed, but for some reason you could expect that some parameter k in your instances is small, then f of k times n to the c for small enough k could actually be better than n cubed if n to the c is actually n, and f of k isn't too terrible. And for polynomial time solvable problems, you can actually even hope for your f of k to be a polynomial function. Right? Whereas for NP hard things, you need it to be exponential, or at least super polynomial. For polynomial time things, the f of k doesn't even have to be an exponential function. So here is a nice exercise. I'm going to leave it to you to think about it, but don't think about it for more than 20 seconds because I'm going to shift to something completely different after this. So this is a good exercise to think about in the next talk. Okay, and this is can you find an algorithm that in an unweighted graph decides whether this graph contains a matching of size at least k in time linear in n, or actually this thing should be n plus m. So n plus m plus poly k. So for small k, this is drastically better than the best algorithms for matching, and it's a super simple algorithm. It really is an exercise. Now, FBT and P, so designing algorithms like this is a relatively new field of study. I think the first people to actually properly define this sort of word were Rolf Niedermeyer, Arcontia Giannopoulos, and George Merzios. And there has been some follow-up work that is quite interesting, so have a look. There are some results. There's lots of tie-ins with fine-grained complexity. This work of trying to upper and lower bound the exponent of polynomial time algorithms for polynomial time problems. But that's what I'm not going to talk about. So what I am going to talk about is optimizing f of k and n to the c at the same time for a classic parameterized problem, namely directed feedback vertex set. Okay, so what is directed feedback vertex set? Input is a directed graph G, so you have vertices and arcs, no self-loops, and you ask, can I find a vertex set of size at most k, so that after I remove this vertex set, what is left is acyclic. So this is a DAG, it has a topological ordering. Alternatively, you want to find a set that intersects every directed cycle in the graph. Okay. The naive algorithm for this runs in time n to the k times linear, because I can try all possibilities for k element sets to remove, and after that, check whether what is left is a DAG. That takes linear time. Okay? So for k equal to 0, this is linear time. For k equal to 1, this is order nm. Yeah. So it was a long-standing open problem whether this problem is fixed parameter tractable, whether you can have an f of k n to the c algorithm for directed feedback vertex set. In fact, when I started my PhD and I asked my supervisor, what problem should I solve if I want to be famous in my field? It was this problem. Okay? So when I started my PhD, it was open whether this problem was fixed parameter tractable. And just a few years after I started my PhD, it was resolved by Chen, Liu, O'Sullivan, and Razgon. They actually gave an FBT algorithm for this problem. So once you have an FBT algorithm, it has the appealing running time of k factorial 4 to the k times k to the 4 nm. So basically, if you forget, I mean, this is the dominant factor in the parameter dependence, so k factorial, and the polynomial factor is nm. And then the question is, what are the natural follow-ups? Well, can you do better? Can you get a better parameter dependence? So can you get 2 to the big O of k? Why do I ask about 2 to the big O of k? Another exercise to think about is to prove that you cannot get sub-exponential algorithm in k, assuming the exponential time hypothesis. This is, again, yet another exercise. So this isn't hard to prove. Another thing you could try to do is to improve the polynomial factor from nm to, for example, linear. That is the best you could hope for. And what is known in this direction? Well, for k equal to 0, it already is linear. That's great. Now, in 1978, Gary and Tarjan showed that you can decide whether you can remove a single vertex from a graph to make it acyclic in linear time. And for k equal to 2, it was open until our work. So in 2018, so next year, so the upcoming SOTA, me, MSR, who gave a talk yesterday, and Saket, who I think gave a talk on Monday, we gave an algorithm with basically the same dependence on the parameter, but now linear dependence on the size of the input. So for k equal to 2, it seems that we are first. Yeah. Of course, now once we have this algorithm, and notice that like the nice thing here is that we traded an n for a k, or we removed an n factor and replaced it by a k factor, so we didn't sacrifice too much on the parameter dependence. So now there could be some hope of actually getting the best of both worlds and getting a c to the k times linear algorithm for DFVS. That would be great, but of course we need to solve this first, which is still a major open problem. Okay, so what is this talk about? I am going to explain to you almost entirely the algorithm of Chen et al., so the FBT algorithm for DFVS, and then I'm going to almost entirely describe how you make it linear. Okay, so the nice thing about the first one is that I get to recap iterative compression, which you've already seen, but it's always good to see it again. And I'm going to introduce a nice technique in the design and parameterized algorithms called important separators. So this is something that if you're doing parameterized algorithms, it's well worth seeing. Now, to get it linear, I'm going to show a recursive compression scheme where this sort of recursive divide and conquer and variations of that have been used quite a bit in order to optimize the polynomial factor in parameterized algorithms. Our particular version of it is a little different from what has been done before, but still you should definitely get an idea of how it is when you get some FBT algorithm, you can try to squeeze the polynomial factor down of it. Okay? So our strategy for getting this algorithm is really to start with this guy and then try to make it better. Okay. So we're going to do iterative compression for directed feedback vertex set. Then we need to define something called the compression version. This is basically the same problem as before. So I give you a digraph G, an integer k, and now I give you a feedback vertex set of size k plus 1. So I give you a feedback vertex set that is almost good enough, but not quite good enough, and I ask you, does G have a feedback vertex set that is good enough, namely of size at most k? I don't think I actually defined this, but I hope you figured out that a feedback vertex set is actually a solution, right? Like a feedback vertex set is the set so that after you remove it, what is left, you have a DAG. Yeah? Okay, so I have one of size k plus 1. I ask you, do you have one of size at most k? And my parameter is again k. And now I will briefly recap iterative compression, which basically says that if you have an FBT algorithm for the compression version, then you also have an FBT algorithm for the original problem with a +1 overhead in the polynomial factor. Yeah? So it costs you a factor of n. So how does that work? Well, let's take the vertices of G, order them from the first vertex to last vertex in some arbitrary way, and then define big Vi to be the set of the I first vertices. Okay? And then I define Gi to be the graph induced by the I first vertices. So G1 is a one vertex graph, then I add one vertex to it to get G2, another vertex to get G3, and so on and so forth. Okay? Now observe that if at any point I decide that G255 does not have a feedback vertex set of size at most k, then G does not have a feedback vertex set of size at most k either, because Gi is an induced subgraph of G, and adding vertices cannot make it easier to delete vertices to get the graph acyclic. Yeah. So another thing that is well worth noticing is that if I have a feedback vertex set to the graph Gi, then, and I call it Si, then if I add a vertex to Gi to get Gi plus 1, and I add the same vertex to Si to get Si plus 1, then or Xi plus 1, then Xi plus 1 is a feedback vertex set of Gi plus 1 because I added a vertex and then I removed it again. Okay? So this really easily gives us iterative compression. So what do? You look at Gk plus 1 and you have a feedback vertex set of size k plus 1. Now assume you have an algorithm for the compression version. You run it on Gk plus 1, Xk plus 1, and either you get an answer, nope, Gk plus 1 does not have a feedback vertex set of size k, then you stop and say, no, G doesn't have one either. Or you get a solution of size at most k to Gk plus 1. You add a vertex both to Gk plus 1 and to Sk plus 1 to get a graph Gk plus 2 and a solution Xk plus 2 of size k plus 1. Yeah? And then, once I have a solution of size k plus 1, I can run the compression version, either get a no answer or a solution of size at most k, and then I repeat, right? I could keep going and say, oh, here I have a solution of size k plus 1. I run the compression version. Either I say no, or I get a solution of size k. Now I can make a solution of size k plus 1 for the next graph. Okay? So I keep doing this. So really, the running time of my algorithm is the time it takes to solve the compression step times n. So all that is left at this point is to find an algorithm that solves the compression step. Okay, so what do we have? We have as input a graph G, an integer k, a feedback vertex at x of size k plus 1, and we ask, do you have one of size at most k? Now, the very first thing you do is you just guess which subset of x goes into the solution you're looking for. And if you guess that a vertex goes into the solution you are looking for, you just delete them. Yeah, okay. Good stuff. Now, some part of x is left. You decided not to delete it. Yeah? And what do you do with stuff you decided not to delete? You make it undeletable. Yeah? So we end up with the following problem. I give you a graph G, an integer k, and a feedback vertex at x. This is the part of x that is left after you removed the part of x that you should delete. Of size still 1 too big, let's say k plus 1. And you now ask, do you have a feedback vertex set of size at most k that is disjoint from the one that you have? Yeah, because now the part of x that you have, you actually made undeletable. Now, we will see an 8 to the k factorial n plus m time algorithm for this problem, which in turn yields a 16 to the k algorithm for compression, because you have this 2 to the k overhead for guessing over all subsets of x. Yeah? And this again gives you a 16 to the k factorial nm algorithm for the original problem, because you run compression n times. Okay. So questions to the overall scheme? No? All right. So let's continue to look at disjoint directed feedback vertex set. Before we do that, let's ask ourselves the following. Is there some clever way to avoid the factor n overhead from iterative compression? Because that is really the only thing that is making our algorithm nonlinear. The compression step actually ran in linear time. We have to run this n times. That's why we get an nm running time. So is there some way of avoiding this overhead? Well, if someone magically gave an approximate solution of, let's say, size poly k, then maybe we could do it. How? Well, instead of running iterative compression from the graph on k plus 1 vertices, what we can do is that we can start with the graph g minus w, where w is our approximate solution. Now, this is a graph with a feedback vertex set of size 0. It's a cyclic, right? So for g minus w, I actually have a solution of size at most k plus 1. I have a solution of size 0, the empty set. Yeah? So then, once I start with this graph, I can again add one vertex at a time to the graph and to the solution, and then run the compression step. So in particular, all I need to do is I need to do w iteration of the compression step instead of doing n iterations of the compression step. So if W is of size poly k, then this is actually exactly what we need. It is 16 to the k factorial poly k nm time. Yeah. But now, of course, how on earth do you get this approximate solution? Okay, so this is, we're looking a bit into the future of what is it we're going to be doing once we figure out how to solve the compression step. We're going to be trying to search for this W. But before we go there, of course, we need an algorithm to solve the compression step. Okay, so let's do that. Suppose we have a solution that is disjoint from X, then I know that after I remove that solution, I have a DAG. There's really like only one thing we can do with DAGs. We can topologically sort them. Yes, okay, we did. All right. Now, in this topological sort, I know that the vertices of X, this disjoint solution that is undeletable, they live somewhere in this topological order. So the orange vertices, they are the X vertices. Okay. Now, what I can do is that I can just guess in which order the vertices of X appear in this topological order. Because there's only k vertices in X, or k plus 1 vertices in X. So guessing the correct order gives me an overhead of k plus 1 factorial. All right. So I do that, I have this k factorial overhead, and after I do that, I add all of the arcs implied by the order. So if I've guessed that one vertex in X comes before another vertex in X, then I add that arc. Yeah. So now, in particular, the set of undeletable vertices, my undeletable solution, forms an acyclic tournament. If the tournament wasn't acyclic, I could say no, because I have a cycle inside a set of undeletable things. So then I definitely cannot find a disjoint solution. So I'm left with the following problem: disjoint DFVS T. T stands for that the disjoint solution induces a tournament. Okay, so I give you a directed graph G, an integer k, a vertex at X of size at most k plus 1, that is a solution, but is slightly too big, and I'm looking for a solution of size at most k disjoint from the one that I have, where the solution that I have induces an acyclic tournament. Yeah?
So is X of size k plus 1?
X is of size k plus 1, yes. So this is... I mean, if X is of size less than k plus 1, I already have a solution of size k. Before I made it, I mean, basically, before I made this thing undeletable, I could have just deleted it, and that would have been good enough. Yes. So X is of size precisely k plus 1. Okay. We will see an 8 to the k algorithm for this problem, which then will conclude the algorithm for feedback vertex sets. Okay. So how do solutions to disjoint directed feedback vertex set T look like? Well, we know that X is this acyclic tournament with a unique topological ordering. And the rest is just some DAG, and it has some topological ordering. And we know that if we remove the solution, then of course I cannot have any path that starts in a vertex in X, then goes down to the rest, walks a bit around and is disjoint from the solution, and comes back to the same vertex. Why not? Well, that's a cycle, right? I mean, I can't have cycles in a DAG. So I better kill those. Yeah, I better make sure that whatever I delete from here will intersect all paths like this, from a vertex down and up to the same vertex. Okay. I also have to make sure that I kill all paths that start at a vertex, go down into the rest, and then come back at a vertex that is earlier in the ordering. Because if I come back here, I know that I have this arc, and then this is a cycle. Yeah? Okay? So these guys have to go as well. And it is not too difficult to check, I'm not going to do this, that these conditions, that killing paths that go from a vertex, stay down here, come back in the same vertex, or start from a vertex, go down and come back in an earlier vertex, that these conditions are necessary and sufficient. Necessary is obvious, I just said it. So checking sufficiency is slightly trickier, but only slightly trickier. In particular, you look at any induced cycle in the graph, and it's going to intersect with the top in at most 2 vertices. Okay? Okay. So in particular, if I have an instance of directed feedback vertex set of this type, if I say that R is the rest, not the solution, not my disjoint solution, then any solution that I look for has to separate every vertex in X from all of its predecessors in X. So X is my disjoint solution. And furthermore, I have to hit all cycles that go from a vertex in X down into the rest and then back up into the same vertex of X. And this is necessary and sufficient. Remember that. Okay, so how are we going to do this? Well, the first observation, and this is whenever you're trying to separate something from something else and also trying to separate something from itself in a graph, this is a common trick if you've ever done programming competitions, and that is you take a vertex and you split it into one vertex that gets all of its in neighbors and one vertex that takes all of its out neighbors. So you just take the last vertex of X, and you know that you want to you want to separate X from everyone before him, but you also want to separate his out neighbors from his in neighbors, because you have to make sure that you can't get back to himself. Yeah. So what you do is you take X and you split it into 2 vertices, one that has all the in neighbors and one that has all the out neighbors. And now what you need to do is, among other things, to separate X out from all of the rest of X. Yeah, that's one of the things you need to do. Okay, so let's look at how a solution interacts with X. Well, consider some solution down here. And now let's look at what X out can reach once I remove this solution. Right? So if I have a graph, I remove some vertices from my graph, and then I start at a vertex and I ask, who can I reach by directed paths without ever having to step on a solution? Right? I mark some things that I can't step on, and I ask, what can I reach? So this R stands for reach. Yeah. Okay. Then, of course, I know that there is some part of the solution that sort of defines the wall or the separator between what I can reach and what I cannot reach. So this is like the out neighborhood of the stuff that I can reach. Okay? So let's call that my separator S prime. And then, of course, the set that I can reach is defined by the separator, not necessarily the entire solution. So this is also the set that I can reach when I just delete S prime from the graph. Okay? So now suppose that I managed to guess S prime. So I managed to guess this vertex set S prime that it has to go into the solution. What do you do with vertices that have to go into the solution? You delete them. Okay. Now, what happens after you delete these vertices? Well, notice that now X out cannot reach anyone in X. Yeah? So in particular, this means that X out cannot possibly be, so X cannot possibly be part of any directed cycle. Because any directed cycle, I either go from the out neighborhood of X and then come back into X, so back into Xn, but I will never be able to come back. Yeah? So in particular, this vertex does not participate in any directed cycles. So he's irrelevant. But that also means that every vertex that he can reach is also irrelevant. No such vertex can also get back up, and none of these vertices can participate in directed cycles either. So all of these are irrelevant. And now what can you do with a vertex that's irrelevant, a vertex that doesn't appear in any directed cycles? Well, you just remove him, right? Because this is the same as removing isolated vertices in vertex cover. They're not doing anything anyway. You just delete them for free, right? So if you have a vertex that doesn't appear in any directed cycles, you just remove them for free and you're perfectly happy. Okay. At that point, you delete both copies of x, both the x and xn, if x out is not part of any directed cycles, and xn isn't either. And then you can continue with the next vertex that is the new vertex that is now last in x, and proceed in the same way. Okay. Take a deep breath, and now we're going to recap what I just did on one slide. Okay. So, what did we do? We looked at the last vertex of this disjoint undeletable solution, and we split it into two parts. And then we guessed some separator that separated the x out, so the one that has all the out neighbors, from the rest of x. Okay? Then we deleted this separator. We put it into our solution, so we paid the size of that set. So we guessed that set, we paid it, removed it from the graph, and then all the vertices that were reachable from x out weren't part of a directed cycle anyway, so we could delete them for free. And the same with x out, and now we have one less vertex in x to worry about. So S is, this is S prime. This should be S prime, I'm sorry. This should be S prime. All S's in this slide should be S prime, I apologize. Yeah, so everything here should be S prime.
What is S prime?
So S prime is some separator that separates x out from the rest of x. So it is this guy. Yeah. Okay. Yeah.
You can't just take the minimum separator because it's too big of an overhead?
You can't just take the minimum separator because if you pick a bigger separator, you might be able to eat up more here, and then more of this stuff gets deleted automatically. And then in the future, when you're trying to pick the next separator, the fact that you deleted more here helps you. So by paying more earlier, you might end up paying less later. Okay. Yeah. So that's why you can't just take that's why you can't just take a minimum separator. And this problem is NP complete. Okay. So I mean, even after guessing the ordering. Yeah. Okay. So what do? We guess a separator. We remove the vertices that become irrelevant because they don't appear in any directed cycles, and then we have a new last vertex, the one that used to be second to last, and we do it again and again. Yeah? Until we have guessed the entire solution. Okay, so now I gave you a really complicated and ridiculous algorithm that runs in the same time as the brute force. I'm still basically guessing all of S, right? I mean, I guess some part of the solution, I remove it. I guess some other part of the solution, I remove it. So all I'm doing so far is just guessing the solution in a convoluted order. But there's still a reason why I'm telling you this, and that is that once we're guessing this solution in this convoluted order, I can actually significantly prune down the set of potential S primes that I need to guess. So how do you do this? Let's compare two candidates for separators. Like, let's call them S1 and S2. So suppose that S1 is at most as big as S2. So deleting S1 costs at most the same as it costs to delete S2. And furthermore, S2 is in the reach of X after I delete S1 or in S1. Okay. So what this means is that S1 is pushed further away from X than what S2 is. Or in other words, when I delete S1, okay, I'm going to delete the intersection of S1 and S2 as well, then whatever is left of S2 after I delete S1 is here, namely, it is reachable from X. Okay, so what does that mean? I claim that if I have some set that is a feedback vertex set, and in that feedback vertex set I'm deleting S2, then instead of deleting the S2 vertices, I could just as well be deleting the S1 vertices. So in other words, S1 is a better candidate for a separator than what S2 is. So whenever I'm deleting S2, I should be deleting S1 instead. Why is that? Well, suppose I delete S1. I pay the same as I would have paid deleting S2. Now, after I delete S1, the entire reach of x in G minus S1 gets deleted for free. So if S2 lives inside here, it's going to get deleted for free anyway. So I pay S1 and I delete all of S1 and all of S2. Yeah? So whenever I'm deleting S2, I should be deleting S1 instead. Okay. So whenever we have two separators from little x to the rest of x, with the property that one is at most the size of the other, and it's pushed further away from your source, then the one that is pushed further is better. Okay? Now, notice that better is actually a partial order on minimal separators, right? If A is better than B, and B is better than C, then A is better than C. Yeah? So in particular, what we only want to try those separators as candidates for my solutions that are maximal elements in this partial order. I want to try those separators so that there is no other separator that is strictly better than that separator. Sort of obvious when you call it better. Now, the separators that don't have any other guys that are better than them, they are called important separators. And a really cool fact that I'm not going to show, but that is proved in the book. The proof is a couple pages. It's not terribly complicated, but complicated enough that I don't want to do it here. And that is that for any pair of vertices, if I look at the set of important separators from one to the other, of size at most k, there is at most 4 to the k of them. So I have now gone down from having to try n to the k different candidates to only having to try 4 to the k different candidates. Yeah? So in particular, I can also enumerate all of these candidates efficiently. So now when I'm trying all possibilities for S prime, yeah, I don't try all of the n to the whatever size of S prime possibilities for S prime. I enumerate all 4 to the size of S prime candidates and try one of those. And that's it. That is actually the entire algorithm. Okay, so, yes?
When you say of size k, it's of size at most k, or it's
of size exactly k. I mean, and so the precise statement of the lemma in order to get a slightly better running time is a bit more complicated and a bit smarter than what this is, but look in the book. Okay? So for now, think of size precisely k. Okay. What basically did we prove? We proved that some optimal solution contains an important separator from x out to the rest. Now we branch on all such separators. Now there is 4 such separators of size 1, 4 square such separators of size 2, 4 cube such separators of size 3, and so on. So if t of k is the time we spend on parameter k, then we end up then t of k is at most 4 times t of k minus 1 plus 4 squared times t of k minus 2 plus 4 cubed times t of k minus 3, and so on. And it's an easy proof by induction to show that this is at most 8 to the k. Okay? I'm not going to do this. So to wrap up, this actually ends up wrapping up the Chen et al. Algorithm for feedback vertex set. You do iterative compression. You guess on the too big solution, you get disjoint feedback vertex set instance. Then you guess the order to make it. You guess the order, you get DFVST. Then you have this 8 to the k algorithm that I just showed you, and wrapping this up together gives you 16 to the k factorial NM time algorithm. Now, in the book, you can get this down to 4 to the k, but this is the dominating factor anyway. So from now on, I'm just going to pretend like this 16 is a 4, because it is. Okay, so this is a good time to ask questions? No? All right. So I have something like 10 minutes, right? I started like 5 minutes late, so I'm going to end 5 minutes late. Oh, that's your punishment for sitting down slowly. How do you avoid the linear overhead from iterative compression? Well, we need an approximate solution of size at most poly k. Then we can do k rounds of iterative compression instead of n, and then we're very happy. So the main question is, how do we get this approximate solution in linear time? Okay, so this is the main lemma of our algorithm that will make it possible to do the whole thing in linear time. We won't be able to find an approximate solution in linear time, but we will find something that looks much more complicated, but is almost as good as finding an approximate solution. Instead of finding a W, we're going to find a W star. Okay? W star, we find him pretty fast in k square n plus m time. He's pretty small. His size is 2k plus 2. So far, so good. But he isn't an approximate solution. He just satisfies one of these three properties. Either, after I delete him, there are at least two non-trivial strong components in G minus W. What's a non-trivial strong component? It's a strong component on at least two vertices. Okay? Or, after I remove him, there is at most one non-trivial strong component. Notice that vertices that appear in trivial strong components can't appear in any cycle, so they are irrelevant. So you can sort of just remove them. So now we're interested in G minus W star having at most m over 2 edges in the unique strong component, right? Because if you don't have 2, you have at most 1. Yes?
Could you repeat what is a strong component?
A strong component is okay. Two vertices are in the same strong component if one can reach the other and the second one can reach the first one. If everyone can reach everyone inside the strong component. Yes? It's strongly connected component.
How is it different from just connected?
I mean, we are in directed graphs, so yeah. Okay. And the last option is that W star intersects with the solution in at least one vertex, or actually that once I remove him, my opt drops by at least 1. It goes from k to k minus 1. Yeah? So this is a much weaker requirement than being an approximate solution. It's like one out of these three things happen. Either removing me decreases the size of the solution by 1, or if I remove him, then a large part of my graph becomes irrelevant and the graph shrinks to something at most m over 2 edges, or I have at least two non-trivial components. So one of those two things happen, and you're going to have to remember this, and I've decided to help you remember this. So these are the three cases. Yeah, these are the three cases of my lemma. Okay. So before proving the lemma, let me show you if we had the lemma, how would we get the algorithm? So we're going to prove that the running time of the algorithm that we're sort of going to design on the go is what we want it to be, 4 to the k, k factorial, n plus m. Okay, so suppose we're in case A, and G minus W star has at least two non-trivial strong components. Okay, then I remove W star. I have at least two components. Pick one of them, and solve DFVS on him. Okay, now notice that my budget for this component is at most k minus 1. My budget for the solution. Because the other strong component contains at least one cycle, so I need to pay at least one vertex over there. Yeah? So I know that the time I'm going to take is t of m, the number of edges in the graph, and KL, which is whatever the size of the optimum solution is there, but no more than k minus 1. Okay? Now, that algorithm runs recursively and produces a solution SL to that strong component. Then, let me remove this strong component from the graph and solve directed feedback vertex set on the rest, on everything except that strong component. Again, my budget is going to be k minus KL, and I know that KL is at least 1, because this was a strong component, I need to delete at least one vertex from it to make it acyclic. Yeah? So now I spent T of M something less than K, T of M something less than K. Yeah? And that gives me some solution to the rest. Right? Everything except for that one strong component. Now I claim that if I take W star, SL, and SR, all of them together, this is a feedback vertex set to the entire graph. Well, if I remove W star, okay, then something is left, and every cycle either lives in this strong component or in one of the other ones. But SL hits all of the cycles that live here, SR hits all of the cycles that don't live in this component. Done. Okay? So this is a solution, and what size does it have? Well, W star has size 2k, SL has size at most k, SR has size at most k, so now I have my approximate solution of size at most 2k, the one that I was looking for. So now I can run W iterations of the compression algorithm. Yeah, and that takes linear time, and then I'm good. So the time analysis for this is, well, first you find W star, that is mk squared time. Then you solve the left part, then you solve the right part. Now you have an approximate solution W, and then you run W iterations of DFVS compress. And then if you stare at this, inequality, you actually see that this is a recursion that basically solves to what we want it to solve to. And really, the point here is that when you branch on, like you have this recursion tree with KL and KR, your K distributes across to the two things, right? If K is 7, then at most, then like 3 goes to this side and 7 goes to that side. Yes? And 3 factorial plus 7 factorial is much, much less than 10 factorial. Yeah? So in particular, this gets completely dominated by the 10 factorial or the K factorial term here. So that's how that induction goes through. Okay. Now, what happens if G minus W star has at most M over 2 edges? Well, then you solve DFVS on that component. Now you have to, now you're running the recurrence on a much smaller component. You get a solution, and now you set your W star, your W to be W star, union that guy. And that's a feedback vertex set because after I remove W star, all of the other vertices that don't live in this component don't appear in any long cycles. And then you do the same. And again, you get some recurrence, and again, you check that that recurrence actually solves to linear time. This time, the reason is that the number of edges that you recurse on drops by a linear factor. Yeah? Okay. Now, again, you have the last case, and you do exactly the same thing. So here, the last case, your solution has size at most k minus 1. And again, you're doing the same thing. You run it on that component, and you put the solution together with W star, and you do W iterations of DFVS compress. And this time it works because when you do your one non-trivial recursive call, you're doing it with k minus 1 rather than with k. Right? So now you're doing a single recursive call with a smaller value of the parameter. Okay, so now that actually more or less, sort of hand-wavy, shows that if we have main lemma, then we have an algorithm. So all that's left is proving this thing. Yes?
What do you do with the trivial strong components? We said that they don't participate in a cycle. Can't they participate in a cycle with W star?
Yes, they can, but we don't care. Because, look at, for example, look at this guy, right? My goal is not to find an optimal solution. My goal is to find an approximate solution W, so that afterwards, I can run W iterations of DFVS compress.
In case B,
In case B,
did we totally forgot about the non-trivial vertices? For example, here.
let's see, this case, yes?
So here you have the unique non-trivial component and SM is a solution there.
So all I'm trying to prove at this point is that W is a feedback vertex set of the entire thing. I'm not trying to find the actual optimum solution. All I'm trying to do is to say that if I remove W star and SM, that is a feedback vertex set. And it is because after I remove W star, the trivial components are trivial. They don't participate in any cycles. So then I have to only handle the non-trivial component, and I do. Yeah? So then I have now an approximate solution of size big O of k, and then I find the actual solution by doing this. Okay? Okay, so proof sketch of the main lemma. It's actually not too complicated, but it's slightly tricky to do in 3 minutes. So let me try to speak really fast. So assume that there is a solution of size at most k. We're just going to drop the situation when there isn't one. And I'm going to pick up an arbitrary edge in my graph, let's say VU, and I'm going to put both U and V in W star. Okay? So W star is this guy that has to satisfy A, B, or C. Okay, I put them in, and either I was lucky and I hit one vertex in my solution, then I really am lucky we are in case C, because removing both U and V is going to decrease K by at least 1. Yes! Okay, so suppose that didn't happen. So then, definitely, if U reaches V, then this is a cycle. S has to intersect that cycle. So S has to separate V from U. So after I remove S, U can no longer reach V. So let's look at the separators from U to V. Now we're going to do something pretty interesting. We're going to compute something called a separator sequence. What is a separator sequence? Let's call Z1, Z2, Z3, and so on separators, naturally, and put them after each other. So what is this set of separators? It's a set of inclusion minimal separators that all have size at most k. Okay? They are pairwise disjoint, and they are nested. Nested just means that things look like in this picture. If I remove Z3, then I can reach Z1 and Z2. If I remove Z2, then I can reach Z1. Yes? From U. So they really are like layered that way. Now, of course, I could potentially have a lot of edges backwards, but all of the edges forwards really go like this. Okay? And finally, we have packed these ZIs as tightly as possible. So out of all sequences of separators that satisfy these 3 points, I cannot find another ZI in between. So I cannot separate Z1 from Z2 using less than k vertices inside here. I cannot separate Z2 from Z3 using less than k vertices inside here. Okay? So I can find such a sequence in linear time. This is just running Ford-Fulkerson a few times. Okay, I'm not going to go into details, but really this isn't all that complicated. Okay, so once we have this guy, what do we do? Well, let me define Zi plus 1 to be the first separator so that the component from U up to him has at least m over 2 edges. Okay? Because as I scan from left to right, I'm eating up more and more edges. At some point, I ate up half the edges. Stop at that point. Okay? Then I'm going to define W star to be, let me make it blink again, U, V, this separator where I stopped, and the previous guy. Okay? Now, let me define 3 sets. A is everything up to and not including Zi. B is everything from Zi to Zi plus 1, and C is everything from Zi plus 1 to V. Okay, we know that A has at least m over 2 edges, so C has at most m over 2 edges. And furthermore, we stopped at Zi plus 1, so A has at most m over 2 edges as well, because we didn't stop here, we stopped here. Okay? We stopped at the first time we ate at least m over 2 edges, so here we hadn't eaten m over 2 edges yet. Okay, so now what are our cases? If W star intersects some optimal solution S, then we are done because we're in case C. Deleting W star decreases opt by 1. Now, notice that after I remove W star, every strong component lives entirely in A, B, or C because you cannot move back, right? You cannot go forward. You can move back, but you can't go forward. So if you go from B to A, you cannot get back to B. Yeah? So no strong component can live across my separators. So in my first case, the solution lives entirely in A. I'll suppose it does that. So I'm going to try to prove to you that the solution needs to live in at least 2 of A, B, and C. So the case I'm trying to the cases I'm trying to get away from is that the solution lives entirely in A, entirely in C, or entirely in B. Suppose the solution lives entirely in A. Well, then B union C are acyclic, right? Because if I look at all of these strong components, they don't contain any solution vertices. Well, if you don't contain any solution vertices, you better not contain any cycles. So then, all of these components, after I remove W star, are trivial components. So all non-trivial strong components of G minus W live inside here, but A has at most M over 2 edges, so we're done by case B. Now, in the second case, again, all non-trivial components live here, but here we have at most M over 2 edges, again done by case B. Okay, what if S lives inside here? This is actually the only interesting case. So how did we pick our ZIs? Between every consecutive pair of ZIs, I cannot separate them with at most k vertices. And this is a set of size at most k, so we didn't separate these two from each other. So there is at least one path from Zi to Zi plus 1 that avoids S. But Zi's are minimal separators, so there is a path from U to that vertex, and from that vertex to V. So now I found a path disjoint from S, from U to V. And S, we assumed, had to be a UV separator. Boom, this is a contradiction. We're getting our skull. Okay? For the last case, we have now gotten rid of the case where S lives entirely in one out of A, B, and C. So now suppose it lives in two. Suppose he lives in A and B. Now, either both A and B have non-trivial strong components in G minus W star, then we are done. Why? Pardon? A, yes, we have at least two components. Great. And if only one of them has non-trivial components, let's say A, then B doesn't have any non-trivial components. And the guy that doesn't have any non-trivial components, you can delete for free. Yes? Which means that after I remove W star, I can remove SB for free. He gets removed for free. So in particular, S minus SB is a feedback vertex set of G minus W, and S minus SB is a set of size at most K minus 1. Yeah? And all of the other cases where you have two guys floating around in A, B, or C are exactly the same as this case. And that's actually it. Okay, so now it's bad form to put both QED and the black box at the end, but given that this was like a one proof long talk, I feel it warrants it. Yeah, so I'm going to do this. Okay, so some conclusions. Both f of k and n to the c are important. We can do feedback vertex set in FBT linear time. It's very open whether you can get c to the k. Nice, even on planar graphs. It's very open whether you can get a polynomial kernel. Again, even on planar graphs. Thanks.